Hello, my dear students, and welcome to our second chapter in this optical systems module. In the first chapter, we have dealt with the optical fibers. The optical fiber, which is considered as the most commonly used guided medium for optical communication. We have discussed together either the optical construction of the optical fiber, I mean the core and the cladding material, the different modes of operation, as well as the different structures, I mean the step index 1 and the graded index 1. Then we have go through the overall optical properties in terms of attenuation, as well as in terms of dispersion. Now, in this chapter, more toward communication, we are going to study how we can implement an optical modulator and an optical demodulator. These two blocks are considered as the two main terminal blocks for an optical fiber. Usually, we connect our optical modulator through the channel, which is the optical fiber, and then the first stage in the receiver is the demodulator stage. Let's now start together this short journey, as I'm expecting to finalize this lecture by one part, while we are considering the optical modulation and the optical demodulation. Now, permit me to start sharing my presentation slides and start this lecture. Perfect. So you can now see my presentation slides. And we can now officially start this second part, this second chapter in our course. As I mentioned, we are dealing with optical modulation, demodulation. I believe we already have introduced the word coherent in our zero lecture, while we are considering a very brief introduction about lasers. Maybe in the next chapters, we are going to discuss in more details the word coherent and its impact. But as we know, we are usually use lasers as a coherent source as an optical carrier for optical communication systems. Okay, perfect. So let me first start with a very brief discussion about what's called modulation. I am quite sure that you are already genius in this topic. You have already studied a lot of modules where you consider the modulation in the communication techniques. So the modulation is simply the process of transferring a baseband signal into a passband signal at a certain frequency. This modulation turns to be digital whenever your message is digital. That's why in digital communication, you usually use what's called the analog digital converters in order to transfer your signal from an analog signal to a digital signal using the three main steps, which are sampling, quantization, and encoding. After that, you will have a stream of binary data, which is a digital form of your message. Then you are going to modulate each set of these binary inputs into what's called a digital symbol. So this digital symbol may include single bit, which usually we call it a binary modulation, or it can be 2, 3, 4, or whatever. So herein you have an M number of bits inside each symbol. Accordingly, we have different types of modulation techniques, I mean digital modulation techniques, such as the pulse amplitude modulation, the phase shift keying techniques, and also the most famous quadrature amplitude modulation, or the coherent techniques. Generally, we can represent any modulation technique, again, here I mean digital modulation technique, by what's called the constellation diagram. The constellation diagram simply is a polar plot that describes the amplitude and the phase of any symbol you are modulating. So, whenever you are considering a modulation diagram, or sorry, a constellation diagram, I'm sorry, you are considering a certain frequency, as the frequency is not observed in the constellation diagram. So, for a binary amplitude modulation. I mean, you have a symbol which is either 1 or 2. Then you have two states, as you can see here. The first with a positive amplitude and the second with a negative amplitude. By the way, this is typically correct whenever you are doing what's called a binary phase shift keying, as you have one in phase and one anti-phase symbol. Then you can increase the number of states, which directly reflect on the number of symbols. So whenever you have 4 states, that means that you can include 2 symbols per state. Here you have 2 different amplitudes, and actually 4 different amplitudes. 2 are positive and 2 are negative. Here you have only 1 positive and 1 negative. Generally speaking, you can increase the number of amplitude levels, and automatically you can increase the number of bits per symbol. However, as a trade-off, as a usual trade-off in the communication system, by increasing the number of levels, you automatically increase the probability of error. So this is a trade-off in any modulation technique. Herein, as you can see, the main variation is in the amplitude. That's why we call this amplitude modulation. So we just increase the number of symbols by increasing states with different amplitudes, as you can see here. And this is the amplitude modulation. The other phase is what's called the phase shift keying, or whenever you are changing the phase. So by increasing the number of symbols, you are using the same amplitude. As you can see, all these points are on the same circumference of a circle. So all these points are equidistant from the origin. That's why we call this shift keying, because phase shift keying, I mean, because you change the phase with the constant amplitude for all symbols. The only difference between these symbols is basically the phase. So this is a 0 phase carrier. This is 45 degree, 90, 135, and so on. So now you increase the number of symbols by increasing these points on the circumference. I mean, by decreasing the delta phase between each 2 neighbor symbols. And this is what's called the phase shift key. Finally, we have, as I mentioned, the most famous digital modulation technique, which called the quadrature amplitude modulation, or the QAM, where we have 2 main components. What we can call the in-phase component and what we can call the quadrature component. And as you can expect, the phase shift between these 2 components is 90 degrees. So one is an in-phase and one is an orthogonal or quadrature to this phase. Actually, all these previous slides are for you some sort of a repetition to what you have already learned in the basic digital modulation techniques in your previous courses. Now, the question is, what is the difference between the digital modulation techniques, or basically the QAM technique, in a normal RF communication system, and whenever we turn to an optical communication system, then what should change? You can easily expect that the main change is the nature of the carrier. As in the ordinary or in the conventional RF communication, you are using a basic sinusoidal signal with RF frequency as a carrier. But in our optical communication, the carrier is no longer a basic sinusoidal. The carrier is a stream of coherent photon, or what's called a laser. So you are now no longer dealing with an ordinary electronic signal. You are now dealing with an optical signal. So you have to use optical devices, or what we can call an optoelectronic devices, in order to perform the modulation technique. So in order to do this, my dear students, what we are going to do is, actually, this is just a more description about the quadrature amplitude modulation. I just forgot this slide. Here we have the in-phase component, the quadrature. So of course, the amplitude is the square root of the in-phase square plus the quadrature square, and the angle is 10 minus 1, the quadrature over the in-phase. Again, this is a basic information you already have learned before in your communication course. Back to our topic, which is the optical modulation. So in order to perform the optical modulation, we have to have something that can transfer these binary input data into some sort of optical variation. So you have to vary some parameter in your optical carrier, which is between quotations laser, in order to be able to carry the message over the carrier. This is done using what we can call the optical modulator. Basically, the most famous optical modulator is this waveguide-based optical modulator. So let's try together to describe this important schematic diagram. Here you have an input energy. Of course, this is some sort of light energy or optical energy, I mean an optical laser source. This is a waveguide. You can deal with it like these waveguides you have already learned in your microwave courses. Later on in our course, we will discuss these optical waveguides as well as the optical cavities in more details. But for this schematic, let's deal it typically like when you have a lossless optical, a lossless waveguide. So whenever the wave propagates, there is a change in the phase, and this change in the phase is equals to e⁻⁻jk times the distance, where k is the propagation coefficient, and if you remember, k equals 2 pi over lambda. So this is typically what you do with the waveguides in the microwave, assuming there is no attenuation coefficient and there is only a variation in the phase while the signal is propagating. And you can easily agree with this description because you know that light can be treated as an electromagnetic wave. So you can treat this optical signal basically the same like what you did for any microwave signal. So here we have an optical fiber, here is the output. And in this stage, you have controlling electrodes where there is an input voltage here that affects the field, the electrical field between these 2 points. So the electrical field now is not constant. It's variable with the variation of this voltage. And in order to include the electrical field in the equation, we are going to include it in the form of the refractive index. So let me describe it. Generally, if you are using air here as a waveguide, which is actually a hypothetical model because waveguides are guided medium, so you are not going to use air, you basically are going to use another material, but let's assume that it's air. If you are using air here, then the k coefficient or the propagation coefficient should be equals to 2 pi over lambda, which is basically the standard propagation coefficient you already have learned, maybe from your electromagnetic courses as well. Whenever you have any different material rather than air, then it will be 2 pi over lambda, let's say lambda dash or whatever. So this is the wavelength inside the material. And this lambda dash is equals to lambda over root epsilon r, where epsilon r is a relative permittivity of the material. So now you can substitute this lambda by lambda over root epsilon r, and you know that root epsilon r is n, so this is lambda over n, so you can put here n as a refractive index. But in this case, as you know, my dear students, this n is constant. I mean, it's constant with respect to wavelength, which is now we are ignoring what's called the dispersion effect. We have already studied in the previous lecture, and we also ignoring what's called the anisotropic property. I mean, we say that this n is constant with dimension along the wavelength, or sorry, along the waveguide. So now n is constant either with respect to dimension or with respect to wavelength, which is of course unnecessary. However, whenever you add this electrical field effect using this voltage, as we just mentioned, this will impact on the material property of the waveguide. And we shall include such the impact on a variation on the refractive index. Here we call this as the effective refractive index, because we include the effect of the refractive, the effect of the electrical field variation in the refractive index. That's why herein I'm using the word or the term delta N effective instead of N. So when it's N, it's constant, but this delta N effective, as you can see, is a function in the input voltage. And L, of course, indicates the length, because if you remember from the exponential term, it's e power minus jk times distance. So distance here is the length of the waveguide, which is of course constant. So as you can see from this equation, which indicates the phasor variation of the optical signal, this equation is function in lambda, which is constant because you are using a monochromatic light source with a certain lambda. 2 pi is constant, L is constant, and the variation in the voltage is indicated in the variation of the effective refractive index. So by varying the input voltage, the effective refractive index is varied. Accordingly, my dear students, if U of t is your message, you can now include the message in your laser by inserting this message terminal onto the electrical field, these electrical field electrodes. Accordingly, any variation in the message will be reflected to the refractive index and automatically will be reflected to the phase change of the laser, or the laser phase change or polarization. This what we call the phase modulator. So we use the variation in the electrical field, which has an impact on the refractive index, and again, which has an impact on the overall phase of the beam, to indicate or to carry the message over the carrier. Now the question is, how we can use this idea, this schematic, in order to design and, for example, coherent modulator. So now this is another example where you have splitted your beam into 2 tracks, as you can see. The first is in phase track, or sorry, the first we will call it, let's call it U1, and the second is U2. So now you have a beam splitter, you split the light into 2 beams, for example, equally weighted, equally weighted in terms of intensity. Then you can, the first half, which is go upward, will be affected by the variation, which is called V1, while the second half, which is called V2, will be go downward, will be affected by the voltage V2, and then these 2 beams will then interfere together to get the output. So the output signal, as I mean this half, because you have 2 halves, the first half is affected with a phase proportional to U1, and the second half is affected with a phase which is proportional to U2. So you have now 2 input streams rather than 1. Here we have 1 input stream, which is U1. Here we have 2 input streams, which is U1 and U2. Okay, so we can scale up this idea. We can go on further and further if we make it like that. So here you have the first block, and here you have the second block. But here you insert another phase modulator with constant 90-degree phase shift. So whenever your light starts to go inside this beam splitter, the first half will go and will be directly modulated using U1 and U2, while the second will be first phase shifted by 90 degrees and then modulated using U3 and U4. Using U1 and U2 again. So there is a difference between the first beam and the second beam by 90 degrees. And this is basically the same idea of quadrature amplitude modulation. To have what's called an in-phase component and a quadrature component. where the difference between the in-phase component and the quadrature component is a 90-degree shift, which can be implemented using this stage inside the green box. So this is typically the design of a quadrature amplitude modulation box. This is an optical quadrature amplitude modulation. So you now fulfill this requirement by inserting this in-phase component and this quadrature component together to form your quadrature amplitude modulation. By the way, I will not going to ask you about the mathematics here. So this is just for your information. You can be just asking about the schematic diagram and the concepts beyond this modulator. Actually, we call this modulator, maybe I forgot to mention it somewhere, where here? Yes, here. We call this modulator what's called the Mach-Zehnder modulator, or the MZM. So this unit, which includes the two states, U1 and U2, we consider it as what's called the Mach-Zehnder modulator, or the MZM. Okay, that's perfect. So this is the general idea of the modulation technique. So you can have an in-phase component and the quadrature component, and you have a phase shift by 90 between this in-phase component and the quadrature component. Okay, perfect. Generally, you can scale up this system. So you can have a multi-level, which is, for example, 16 QAM or 64 QAM or whatever, by repeating this block diagram. As you can see here, this is a beam splitter. So you have a laser source, which is a carry. This is a beam splitter, so you split the beam into two stages, and then you can have an input here. This is the first message, and this is the second message, and then you can combine them again over an optical fiber. So you can scale up your system in whatever dimension you need by repeating this MZM modulation block diagram. Okay, what about the detection? Usually we are detecting the light intensity of a laser using a famous photodiode structure. Maybe later on in this course, we will have a very brief description about the physics or the semiconductors of this photodiode structure. Actually, somehow this is outside of the focus of the course. Usually this is delivered in the optoelectronic course rather than the optical system courses. But as far as your curriculum only include one obligated course related to optics, that's why we are going to make a very brief description about it. But herein in the photodiode, we can measure the intensity of the light as well as its phase, and then you can demodulate. So you can demodulate this outer beam and return it back into voltage. So basically, what we are going to do is you are measuring the intensity and then converting this intensity into a variation in voltage. This is what is done. Okay. Finally, as I mentioned, this is somehow a very short lecture. So this is just a brief introduction about modulation and demodulation technique. Maybe later on in your advanced courses, if you join some master programs for optical or something like that, maybe you can know more about it. But generally speaking, as in the RF communication, we have sources of error or sources of noise. Similarly here, we have also some sources of noise, mainly in two regions. The first is what's called the wavelength or the frequency mismatch. I mean, for example, you have a laser that should work at, for example, 800 nanometer infrared laser or red infrared laser. In this region, if the generated beam from the laser is at 810, then there is a big shift in your calculation, because if you remember, my dear student, your phase is inversely proportional to lambda. So you did your calculation for a certain lambda, but the real system operating at different lambda. So this is a problem. Another problem, which we are going also to discuss in the next chapter, which called the wavelength, the line width of the laser. Because usually you are considering the laser as a 100% coherent light source. That's why in this equation, I told you that lambda is constant because the laser is a coherent. It's operating at a certain wavelength. It's a single coherent structure. So, for example, it's 550 nanometer laser. However, in reality, there is nothing called a pure 550 nanometer laser. This laser should have what's called a line width. I mean, it emits light plus 500 nanometer and minus 500 nanometer with a certain line width. Again, we will discuss this in more specific details in the next chapter. So this is another source of error. Another source of error is considered in the phase error. Whenever you are transmitting with a certain phase, and due to some variation or some losses or some attenuation or even some dispersion in the optical fiber, then you have some phase change, and of course this phase change can cause or can interrupt error to the system. So these are basically the sources of error for an optical communication system that can affect your demodulation stage with respect to the modulation stage. Finally, in order to try to protect yourself, herein we are using what's called the pre-correction or the protection techniques in your modulation. Usually this is implemented using DSP units, which is totally out of focus for this course. Maybe for those who are interested in DSPs, they can learn more about that by accessing different resources. I will supply you with a lot of these extra resources if you are interested in this matter. Okay, so this is the termination of this short lecture, this short chapter, dealing with optical modulation, demodulation technique. This is just a very brief intro about that topic. Maybe, as I mentioned later on, you can learn more whenever you are interested, either through your graduation project or through your any advanced postgraduate courses. In the next chapter, we will make a big turn in the module. Now, this is the end for the communication stage, where we have dealt with optical fiber as well as optical modulation and demodulation. In the next stages, we are going to deal with the laser, which will be the main topic for the rest, maybe 6 to 7 lectures in this module. Thank you very much for your concentration, and see you later on in the next chapter under the title Atomic Radiation. Thank you very much.